Welcome everybody. As the slide title here lets you know, we're going to talk about averaging today, and specifically averaging in SimCenter Test Lab. In ways of an agenda, real simple, we're going to have a really brief basic background, describe what we're doing and why we might want to do it. Then we'll talk about the various averaging types that you might find in SimCenter Test Lab. These include a linear average, an energy average, and then our friends min and max hold. There will be a small caveat to the energy average. There'll be sort of a bonus section for energy. It has a special kind that you can do. And then we'll take a look at some data in the software and just see kind of the effects. There'll be examples going through here, but we'll do the software at the end here. So background, when and why do we average? Well, certainly when we have something like you see here, I've got 3 runs of maybe a test where I have an overall level versus time. And you see some differences in run 1 to run 2 and a run 3. And while this might be helpful information, maybe I want to boil down the trends I see here to a single number so I can more appropriately compare run 1 to 2 and 3. So if I do that, I can compute an average, and I can put this right in the legend of Test Lab. It'll compute this average for me right here in the legend. And I've gone ahead and added some lines here. It shows me, okay, so the blue run 2 is about 1.5 dB higher on average than run 1. So it takes these trends that I see developing over time and boiling them down to a single number. So this is an amplitude versus time scenario. All averaging is all about amplitude. That's really all we're ever talking about, but there are different ways we can look at amplitude. In this example, it's an overall level versus time. You could also have something like this where it's frequency spectrum, so frequency axis down here along the bottom, and then we're watching as we progress through time here. This could also be RPM. But we're computing a full frequency spectrum for our test as the time goes on. So how do we handle this in terms of averaging? Well, essentially, we've got a bunch of frequency spectrums. You see some changes as time goes on. So when I average, I'm going to combine all of these frequency spectrums, and I'm going to average them. And I'm going to end up with a single frequency spectrum, or amplitude versus frequency. And this is what you'd call an average spectrum. How does this work? Where did this amplitude, let's say at 419 hertz, come from? It's equivalent to, if you want to go through this exercise yourself, you can add a processing frequency cursor in your waterfall or your color map. So this is going to basically be a cursor. I put it right at 419 hertz. And if I make it a processing cursor in Test Lab, it allows me to then split out the amplitudes solely for 419 hertz frequency line as we progress through time. Okay, so now again, just like our overall level versus time, I have an amplitude versus time plot here that I've made with my processing cursor at 419 hertz. So this is the amplitude of the 419 hertz frequency line as we go through our test. And I can create an average, just like I did with those overall levels. I can create an average. What's the average amplitude of this frequency line at 419 hertz? And we see I get 0.018 Gs of acceleration. So when I go back to my waterfall and I create an average spectrum, here's my average spectrum in blue. I put my cursor right here at 419 hertz, and I look at the amplitude of that, and it comes out at 0.018 Gs at 419. So what the software is doing is this for every single frequency line in my test or in my FFT, it's going through and saying, what's the amplitudes of this frequency over the entire test? And then I'm going to average all of those individual amplitudes. So I'd just like to take a minute and separate something like an average that's occurring over time versus when I look at an average in the frequency spectrum like this, the averages have kind of been done behind the scenes, and I'm doing so for each individual line. So when we go to compute this in Test Lab, we have a couple different options. This is what it looks like in Test Lab Classic, where I say I want to compute an average spectrum, and it'll say, okay, what kind do you want? and you'll have these choices, and these should look familiar from our agenda. They are the energy average, the linear average, the special case of the energy, which is an exponential average, and then our friends min and max hold, or minimum value and maximum value. So let's take a look at these one by one and get to know them a little bit better. So for a linear average, it is just like we learned in elementary school or maybe junior high. I'm not exactly sure. It's been a long time since both of those for me. But we essentially sum up all of our values from 1 to however many we have. We add them all up and then we divide by however many we have. And that's a linear average, pretty straightforward. This will be the default if you compute a frequency spectrum in terms of a spectrum format as opposed to an auto power. If you choose spectrum, this will be the default offered to you if you want to then average that spectrum. It's commonly done for noise removal when the phase and amplitude information is important. So if you imagine doing an impact FRF on a structure and you want to take 100 averages, and you do that to essentially keep all the stuff that's really there, all the response that's really there coming from the structure, and average out all the random noise that's in the background or in your signal chain, noise from the structure or electromagnetic noise or something like that. So we take a bunch of averages so that the real data stays with us and the random data goes away. It's a linear average of the values. And if you have a complex number like a spectrum where there's a real and imaginary component to that, those real and imaginary components will be averaged separately. So all the reals will be averaged and then all the imaginaries will be averaged, and you'll end up with an average complex number. Energy average, a little bit different, obviously, that's why it exists, but this is analogous to doing an RMS, or a root mean squared, where you see, again, there's a summation of our values from 1 to n. However, we're going to square those values before we add them up. And then we're going to divide. So we square all the values, we add that up, and then we divide by the number of values, and then we take the square root of that divided sum. This is a root mean squared. So when you do an RMS calculation, say for that overall level versus time, this is what you're doing in test lab. And as a function of the way this is formulated, because I'm squaring all of the values before I sum them up, the largest amplitudes are going to get more weight than small amplitudes, right? Big numbers, when they're squared, get even bigger than small numbers when they're squared. And so they take up a proportionally bigger section or weight of the average. This will be common for acoustic applications. If you think of sound power from sound pressure, like ISO 3744, you're measuring pressure at all these different microphone positions around your object, and we want to average that pressure, right? And then divide it by the surface area over which that occurs. That average pressure we often do in an energetic average, so that, again, if you have any really high values, those affect your average pressure more than small amplitudes. Because it's an auto power, or because it's being squared, the phase is obviously being removed for the calculation. And so an energy average will be the default for auto power functions in test lab. Okay, so if you calculate an FFT as an auto power, and you say I want to average those, it's going to assume you want to do an energy average. So let's take a look at some simple examples with these amplitude values. We got a really simple set of 1, 3, and 8, and we're going to compute the linear and energy averages of both of these. So again, real simple. I add them up, divide by 3. That's 12 divided by 3, or the linear average of these values is 4. If I do the same, but with an energy average, obviously I'm squaring all of the values, then dividing by 3, and then taking the square root of that, and I get 4.966. And so you see this 8, being bigger than the 1 and the 3, more than double the largest other number. That guy dominates this average much more than it does the linear average, okay, because I'm squaring those terms. So you see the effect when I have a different amplitude, or an amplitude that's different from the others. So let's look at another example. So maybe this is the sound pressure versus time of some transient event. We've got some low-level background sound pressure values progressing through time here. So this is a time axis, or the number of data points that I'm including, not frequency. And you see I'm at a low level, 0.5, 0.1, pretty small. And then all of a sudden my event happens and I get a magnitude 3.5, 4, significantly different. Comes down, then goes back up, and then it kind of goes back to the lower level. So if I were to calculate a linear and an energy average versus data point, so again, as we're progressing through time, the energy average is in the dashed yellow line and the linear average is in the gray solid line. And as these data points get added, you see when all the values are this low, sort of background noise level, the averages are pretty similar. But as soon as we have a big value pop up, the transient event happens, my energy average differs more significantly than my linear average because I'm squaring these high values. So as I progress through time, you see my energy average sort of stays higher than my linear. Which is the right answer here? Unfortunately, there's no right or wrong answer. It is what is most appropriate for what you're trying to do. If I'm assessing the overall noise level of a door slam event or some transient event like you see represented here, maybe the energy average is going to be more appropriate for me cataloging this door versus another door that might have a lower energy average because this peak is smaller than this one. And that energy average is going to capture that difference better for me, say. Now, this is, again, progressing through time and how this average value progresses as I add these red data points. If I were to say the red is my whole data set and I just want to calculate a single number, just like I did with those overall levels in the very beginning, I don't want to progress through time. I just want to say for this whole 40 data point test, what's the average value? And you see my energy and my linear are different, again, because of that squaring function. Now, if you notice, where does this single value come from? Well, it's exactly the same as the final data point, right? So I'm changing these averages as I'm adding data. Once I've added all my data and I get to number 40 here, this value right here, I'll leave my mouse on it, I page down, and that is this value. So the single number for the whole data set is equivalent to the final moving average, if you want to think of it that way. So let's look at one more example. So here we have, again, an amplitude progressing through time, or data points here. And you see, essentially, I'm in the hundreds, right? Whatever this unit is, not really important. But the lowest on the scale is 550 and the highest is 800. So 550 and 800 are a heck of a lot closer together than say 0.1, 0.2, and 4. So if I calculate, again, the moving average, linear and energy function versus data points, you see that essentially there's almost no difference. You have to get to at least second or third significant digit before the linear and energy averages vary very much. And so it's because all the data that I'm giving it is roughly in the same ballpark of amplitude. Whereas in that transient example, we had bigger differences between them. Our last partners here are max and min hold. And so how does this work? Well, essentially, for each one of these frequency lines, like from 0 to 2000 hertz in this case, the software is going to go through, and if we go to our old friend 419 here, if I'm doing maximum hold, it looks at the first data point and says, okay, it's 10, let's say, waits till the next data point. If it's now 11, it throws away the 10 and keeps the 11 because 11 is bigger than 10. It keeps listening, and you see the value goes up pretty significantly here. So it looks at the whole test through time for each frequency line and just keeps the maximum value. Pretty straightforward. Similar with the minimum hold, it's the smallest value at each frequency line throughout the entire test. Pretty darn straightforward. So if we look at this run up, again, we're going to do a max and a min hold. We're going to get an average versus frequency. And you see I have a max and a min. And then I put my linear average right here in the middle. And I think this is actually an energy average as it's closer to the max. But essentially you get this window, right? This is the smallest amplitude seen at every frequency line This is the largest amplitude seen at every frequency line. Even if this one happened at time 19 and this one happened at time 1, it doesn't really matter. All it cares about is the largest and the smallest. So that's min and max hold. Pretty straightforward, but might be useful for you. So now I'll show you some stuff in TestLab. If I look at this waterfall that we've been looking at, we see the amplitudes are increasing as I go forward in time. We're getting toward the back of our waterfall here, and the amplitudes are increasing at least at several of the frequencies. And if I look at the time domain data, this is a single channel of acceleration, and I'm just computing FFTs as I go along. You see the time data, the amplitudes in the overall sound pressure signal get bigger as they go. And so the data at the end of the time trace is at a higher amplitude and should be dominating our average more so than this low level stuff in the beginning. So let's take a look at this front back. And so I'm going to look at a couple of the different averages. So if you can see on your screen, I've got an energy average, a linear average, my min and max hold here. And so if I look at the energy average first, I see this is sort of the average value. I'm going to put this in amplitude again. So here's my linear average. If I compare that to my energy average, we see at these peaks, the energy average is more different or more dominated by those elevated amplitudes than it is all throughout this sort of lower level stuff, where we have a lot of excitation or response in our acceleration signal. Again, this is frequency. So at this resonance or whatever's going on here, we got a bigger number. So when I square those, it's going to dominate the average more. So that's linear versus average for this whole 19-second run up. Then if I put in my max hold, you see these are the highest values at every frequency line. My min hold here, it's hard to even see it, right, on this linear amplitude scale. So I'll go ahead and put it in decibels. And this is kind of what you expect. The average shouldn't be equivalent to your max hold, and it shouldn't be equivalent to your min hold. It should be somewhere in the middle, and that's exactly what we see. Again, depending on your usage, energy or linear, both are maybe appropriate. In this case, I tend to like the energy average just because I want to sort of penalize those higher amplitudes more than just count them, because those are more of a problem for me than just counting them the same as every other amplitude like the linear average does. That's those average types. If you want to see how I calculated those, essentially, so you see I have a linear average, an energy average, min hold, and max hold. So I just take my time data, that acceleration signal you saw, I just take that and plop it right into each one of these processes. And you see I also did some exponential energy averaging at 10, 50, and 90% EWF or weighting factor. And we'll take a look at that data next. But I wanted to show you essentially how this gets calculated. So in NEO, it's just called a spectrum average. So if I add this spectrum average, I can look at the properties, and essentially averaging type, you see it says average, exponential, min, and max hold. And you notice it doesn't give me the option to do energy or linear here. And this is where that default selection comes in. So because I have an auto power in my function class, when I just say average, it's going to automatically do an energy average because of this function class of frequency spectrum that I want to calculate. If I change this to spectrum, this will now do a linear average, again, for those complex functions. The real and imaginary will be done separately. If this is a little bit confusing to you, you can look in this help and it will explain this to you. Again, we're trying to error proof this a little bit for you so that, when you are feeding an auto power spectrum, you want to essentially do that energy average because of the way that the function is formulated. And similarly, if you're trying to maintain some phase, you want to keep those complex numbers separate and keep that phase. So again, it has to do with this type of function. Then I can select an exponential if I want. Here's my exponential parameter. etc. All I did was create several versions of this. And if you don't know, how did I get this called? Because if I just add multiple spectrum averages, I'll just add a bunch here. And they just get called spectrum average.1 and spectrum average.2. That's not particularly helpful for me. And so I can come in here, and for this first one, I'm going to set it up to be a linear average. So I set this to spectrum, you see, and then did average, and I come up here and I just name it whatever I want. So this will come up in the pivot table as your creator data point. So that's how I like to look at my data, is I want to know it's a linear average process or method that I sent it through. Similarly for energy average, min and max hold. So when I go back over here to my desktop, you see I get these energy average, linear average, because I'm in this DOF ID versus creator. If I look at DOF ID versus function, there's auto powers in there, but I can't tell them apart. So this isn't as useful for me as looking at creator. If I go over to run 3, this is where I did those exponential weighting functions. And again, just to mention, there's this thing called the energy exponential average, and its formulation gets a little bit more complicated, where you have this exponential weighting factor. And so TestLab will ask you for a percentage, where this EWF, or exponential weighting factor, will be a percentage between 0 and 100. And you're telling the software essentially how to break down the weighting between old data and new data, okay? So real generically, the most recent samples with an exponential average will be weighted more heavily than the pre-existing average. And to sort of break this down, you see this data that we just looked at where it's kind of going up and down. And I've plotted, the function is in red, and then I have an exponential weighting factor of 0 all the way up to 100. And you see if I do 0%, that's essentially saying I want you to give 0 weighting to pre-existing data. Okay, so the red and the 0% are exactly line on line. It looks at the new piece of data and says, that's my 0% exponentially weighted energy average. As each data point comes in, it becomes the new 0% weighted average. The opposite end of that spectrum, where you're saying, give 100% of my focus to the oldest data we have, or the pre-existing data. And so if I set this to 100, it essentially ignores all of the new data and just keeps the first data point. If you go out to 5 or 6 decimal places in Excel or something, you do see this amplitude is moving a tiny, tiny amount, but essentially it's very, very insignificant. Okay, so if you have 100% weighting factor, you're saying the first data point is all I really care about, and then each percentage point in between is somewhere in between those. And so you see the effect of 50% is this sort of light purple, where it's not going to the extreme peaks, but it's not falling as quickly as the original data is either. If you are a financial stocks person, you probably recognize this as the exponentially weighted moving average. This is very typically calculated for stock prices versus time, and you can select that exponential weighting factor to represent how responsive you want to be to a stock price change, essentially. Just to break this down a little bit for you, because it can be confusing when I look at something like this, my eyes kind of gloss over and think, I don't know, it's some complex thing. I don't really need to understand it. But if we see T is defined here, and essentially the larger I make my exponential weighting function, the larger this value gets. So if I put a 1 in here, or 100%, technically this goes undefined, and so I need to make it like 99.99999%. This gets close to 0, T gets incredibly large. So if you look at the effect of these two polynomials, so I have my newest data point, so the newest average, this bar means average, so my newest data point average is equal to this 1 over this T times my existing, or my most current data point, plus some other coefficient times my pre-existing average. Okay, so my new average is my new data plus my pre-existing average. So 1 over a huge number essentially gets 0, right? This is a million. 1 over a million is essentially 0 times the new data, where a million minus 1 divided by a million, this is essentially 1. And so this is why my pre-existing average for 100% just stays the whole time. Whereas if I make this something small, like 10% or whatever, then this polynomial coefficient gets bigger and this one gets smaller. 0 is, I care about the most recent data most. If it's 100, it's equal to the first sample. So I think of this as, how much do I care about the old data? 0% or all of the way. So in TestLab, I did 10%. So I only care 10% about the oldest data. So if I drop this guy in here, you see he's pretty close to this max value. Most recently, remember, if you look at the time domain, most recently we're at some pretty high amplitudes, at least in terms of overall pressure, right? And so I care 10% about the oldest data. That's going to be a higher level than maybe 50%. Although 50% you see is right there on top of 10, and then I have 90. And you see all of these essentially are right in the same ballpark. And that has to do with how much this old data is being updated through that process. And I'll show you that here. So if I go to name, and I look at my spectrum map. And so essentially I have the individual FFTs at all of my timestamps here. And you can see I add my very last FFT in there. Boom, that looks a lot like my 10%. It looks like all of them, but if I remove some of these other guys we don't care about anymore, min and max hold aren't too important. I'll leave the linear in there just for fun. But essentially, this very last average, pretty similar. As I get older and older, this will essentially start to trend more toward one of those percentages than the others because I care less and less about it. But you see, I have to go pretty far back in terms of FFTs to have the amplitude really change significantly. I got to go all the way back to very old data, where now I'm starting to drop down here, right? Again, this is dB value. So if I go right to the very beginning, first second in, all my levels are low. And so even at 90%, I'm still being dominated by those higher amplitudes because of the difference between the largest and the smallest. If you look in amplitude or linear amplitude, not in decibels, I think these trends make a little bit more sense. But again, is there a hard and fast rule I can give you about which percentage is most appropriate? I cannot. So feel free to play around. And if you come up with something or you know something, I would love to hear about it. That is all the information I have to offer you today. I appreciate your attendance. You see my contact information or my email up here.